but to do the whole practice exam wasn't the point of that. And so you want to treat it as a test. We can, if you know similar problems in the book or something, we can go over those. So one of the things that you're going to encounter if you continue in science is there's going to be no solutions manual. There's going to be nobody you can ask, for did I do this right or did I get the right answer? And for some that's very it's very uncomfortable. Not to be able to ask somebody if they did this right or not to be able to look up the answer in a solutions guide. But you have to think about this. Once you start doing science, nobody's going to pay you to repeat a homework problem that somebody else has already solved. Somebody's going to, if you're going to work in some kind of field or work in some kind of job, you got to be doing something new. Doing something new, then you have to be able to go through the problems yourself and say, did I get the right answer? You have the book there. You can always check your answer in the book. However, some of these might be tricky, so we can take a look. And so you want to start doing that. You want to start doing, did I do this correctly? Not by did I do this correctly by asking, but did I do this correctly by you checking the answer yourself in whatever book or whatever resources you have available. The other thing is the peer review. Lots of times people will come up, okay, they have the answer, but in science everything's peer reviewed. So what you do is you send out your answer in the form of a report to different people working in the same field, and then they'll review it and check it. So it's part of it. But whether they know the answer is a different story. They might have suggestions on that type of stuff. So what you do is you go like the first problem, delta G value equal to 0 means what? When the system reaches equilibrium. Does it mean gases will be at 1 atmosphere, solutions will be at 1 molar, and temperature will be at 298?
C.
Gases will be at 1 atmosphere, and solutions will be at 1 molar. B. C. K will be equal to 1. Is that true? This is very tricky. It's not true because how to make C true? Is C, could you make C true? Right now C is false. K doesn't have to be equal to 1. Delta G is equal to 0. In fact, what we did was we solved, yesterday we solved, we're working on that problem, where we set delta G equal to 0, but K we set at 6.0 whatever, about 7 times 10 to the positive 15, I think it was, or something. Delta G equal to 0 just means it reached equilibrium. But why might you have thought C? Well, you probably thought C is because delta G naught. Delta G naught is equal to minus RT ln a K. Right? And so the situation here is this. If delta G naught equals minus RT ln a K, then if delta G naught is equal to 0, then K must be equal to 1. But I'm not asking about delta G naught. I'm asking about delta G. Delta G and delta G naught are two totally different things, right? Two totally different things. And so C would have been correct if I asked delta G naught. Would A have been correct if I was asking about delta G naught? No. A wouldn't have been correct because you could have it at different temperatures, right? What about B? If I were asking about delta G naught, would B be true or false? See, okay, this is what you want to do. I could tell you the answer. The answer is D. Right? What are you going to do? Are you going to memorize that answer? The situation is you have to put a lot more thought into this. When you put a lot more thought into it, then you can see clearly which one is the correct answer. Versus memorizing the correct answer and not knowing about the other answers. So this is what I mean by self-checking. You can self-check these if you understand it well enough. Either process of elimination or just selecting the right answer. But if this were delta G naught, then both B and C would be true. But it's not delta G naught, it's delta G. So it might be, it might not be. Depends if we're under standard conditions or not. What other problems on the test were you uncertain about?
So the ICE problems, that's when you're given a value of K and you're trying to find the concentrations?
Okay, when we're given a value of K and we try to find the concentrations, that's chapter 15. And so you don't have to worry about that for this test. Given a value of K. However, we still do ICE for like this. This one we try to figure out what the K value should be and then determine the temperature. That's a little different than given a value of K solving. I did the given a value of K in solving for the concentrations or the pressures at equilibrium, just because we're behind, and also is chapter 13 and 15 isn't so well integrated. Chapter 13 used to be chapter 19. They didn't change it enough. And so you needed some chapter 15 stuff for chapter 13. I don't know why they changed it. I like the original chapter 19 placement, but it's okay. Otherwise, chapter 13 becomes too much. Chapter 13 becomes a combination of chapter 13 and 15. Chapter 15, though, is going to go very fast. All we're going to do is we're going to look at something called Le Chatelier's principle and do some calculations, ICE calculations. That's it. All right. So here in number 11, we did this problem yesterday, but different different. Rather than having 90% converted, we asked for it to be 99.999% converted. Exact same problem. That's number 11. And it's a little different than what we're talking about. But like number 2, well, this is the first one. We'll look at it, this practice test. But for the remainder of them, you should, every semester somebody asks me for the key for this, but it's open book. Why do you need the key? You have your book, you can check your answer that way. And then what that does is it builds confidence in yourself. It builds confidence in yourself so that you say that you don't need to ask somebody up. You're always looking for somebody higher than you can ask. Did I do this, or more experienced than you? But it just builds confidence that you can come up with the answer. And, so number 2, somebody asked me about this yesterday, not in this class, but the other class. This one, they're very confused. The aluminum 3+ should be the lower entropy, but somebody else told them no. But number 2, do you guys have number 2? Yeah. And then I asked them, do you know Appendix D? Appendix D has, do you know how to use it? No, they didn't know how to use Appendix D. Or they didn't know that it's a tricky table to use in comparing the numbers. You can't just directly compare. And so then I asked them, do you remember all the talk about the Fahrenheit, Celsius, and Kelvin? And no. So then I told them just to look in Chapter 7 because it's discussed in Chapter 7. If you want to see what the Appendix D is like, you can look in Chapter 7. So that's when it's first discussed about ions, cations, anions, neutral species. But what's the correct answer here? Yeah, the end. What's that?
What is L3 plus have negative entropy?
Why does it have negative entropy?
Yeah.
Because because it's more ordered than 0 entropy. So it's lower entropy than 0.
Okay. That's kind of like the question about negative energy.
Right. So negative energy doesn't exist. It's like negative grams. Can you weigh negative 10 grams of sodium chloride? You can't, but I've seen negative grams on people do the calculation. They made some kind of sign error and they come out with some negative number, like negative 10 grams. I've seen negative Kelvin come up on exams too. This is because they don't even think about the number they're calculating. They just want a number and then write it down and then be happy that they're done with the problem. But yeah, negative Kelvin, I've seen that. On tests, I've never seen it in the book though. But why would you see negative entropies in the book? I mean, come on. There's no such thing as negative entropies, right? How can you be more ordered than a perfect crystal? I mean, how many ways do you have? If you think there's only one way to order a perfect crystal, then, well, and so why do we have negative? Somebody, explain it to me. This would be like a test question. I was thinking about, this would be like a test question to tell me how Appendix D is organized in the thermodynamic table, in terms of cations, anions, and neutral species. Can you? I don't know how many hours I spent talking about Appendix D in cumulative. In Chem 1A, I've probably spent like 3 hours or more talking about Appendix D. In Chem 1B, I spend less time. I figure most people have used it quite a lot by this time. So, but still, I spent over an hour. Didn't I spend over an hour talking about Appendix D? But I was listening to. There's this guy, the Guinness Book of World Record holders, the guy who memorized the most cards. He memorized pi. I think he memorized pi to 20,000 digits or something like that. So I was listening to his talk, and he was talking that he had average memory. You know, his memory is nothing special. But what he did was, and he said he struggled with tests and other things, but he had to learn some techniques for memorization. But he came up with something that I thought, wow, that's so true. He said, like, in 3 months, you know, let's say you put in an hour of learning, 3 months later, you only remember like 12 minutes of it. So 48 minutes is completely wasted. That's 48 minutes of that hour is gone, wasted, no more. And so he said, you know, reason is you learn and then your memory reaches this peak, but then it just starts to decay after 1 day. He said after 1 day it's 50%. I heard more, like 60% after 1 day. You know, after 1 week it's way down. After 3 months, you know, you're down to whatever percentage. And so he was saying that the only way he remembers stuff is he has like the 1-7-1, something like that, system that he uses. And that is, after learning the material, he reviews it 1 hour after. And then the next time he reviews it is 1 week later, he reviews it again. And then he switches to a 1 month cycle or something where he reviews it every month. That way he says he doesn't forget the information. Me, I had to do it more. I did it like immediately, like 10 minutes after class or 5 minutes. I tried to keep a block of time free after class. I didn't like back-to-back classes. If I had back-to-back classes, it's 1 hour. I forgot a lot of stuff, and I don't write fast, and so most of the stuff was in my memory. And then I'd write it down right after class. You know, the stuff in lecture that I couldn't write down during class, I'd write after class because it's still in my short-term memory. But after 1 hour, I would lose a lot. And so this is why I tried to schedule nothing after class so that I can go back and review. And then I would review immediately after class and then every day after that. Because on a quarter system, you know, it's 10 weeks and then the final exam. So if we were on quarter system, it's like halfway, almost halfway done. We'd be going at a much faster pace. You know, I'm going too slow now, but I need to pick up the pace. But anyway, it's like this, you know. When it comes time for the exam, how much of the stuff did you forget? You know, most of it. Unless you review. And so, did somebody remember this? Why is it negative? Negative entropies are not possible. Why is it negative? Because it's not an absolute entropy. You know, it's like this. Negative pressures are not possible. Well, in the absolute sense, it's not possible, but in the relative sense, it is possible. When we have gauge pressure, is relative to an arbitrary zero. The arbitrary zero on gauge pressure is set at atmospheric pressure. So when your helium tank runs out and you can't fill any more balloons, is the tank really empty? No, it's not empty. It has whatever atmospheric pressure is, let's say it's 1 atmosphere, it has 1 atmosphere of gas in the tank, right? There. And so somebody tell me what the entropy of cation is referenced to, please. What is aluminum reference to? This is like PSI A, this is like PSI G. We could have negative gauge pressures. Negative gauge pressure is called a vacuum, but it's not really negative. It's not, they don't have negative collisions. So if you're at a pressure of 0 in that helium tank, you can suck out all the remaining helium in that tank and get to negative 14.7 psi. That's sucking it out. But, you know, well, anyway, how about this? Go back to chapter 7 and take a look at that, because that'll go into it in more detail about how the cations are referenced. You can see it there. It has to do with this stuff. But there's more to discuss. So we can come back to that later. All right, number 3. This is because of the old placement of this. This is from chapter 19. And so the test is going to be a little different than your test because, do you see, the ordering and so I covered a whole bunch of other chapters before I got to this point. And so this is something I only talk about on day 1. I don't know. This is on the PowerPoint slide on the first week. Anybody remember why or what this involves? A mixture of air and methane reacts very slowly at room temperature because it has a small driving force? No. That's not the case. It has a large driving force at room temperature. It just needs a little bit of a kick. And so there are 2 things. So this is back in the first week. There are 2 things when we predict a reaction. The 2 things we have to consider when we predict a reaction are thermodynamics, which we're doing right now. Thermodynamics is a driving force. The other thing we need to know in order to properly predict a reaction is the kinetics, how fast the reaction occurs. And so the correct answer reacts very slowly because delta G naught is close to 0 at this? No. Delta G naught is highly positive? No. Delta G naught is highly negative. Once I give that spark, it reacts very quickly. Even though the gases are initially at room temperature, it reacts very slow. Because delta G naught is highly negative, but that's not why. So it's none of the above. It reacts very slowly because of kinetics, slow kinetics. There's a pretty big driving force. And so when we do this later on, the driving force is this drop down in energy, so it should be all downhill thing. But initially, in order for this to react, there has to be a collision, and we break bonds. That collision and we break bonds means there's a little hump here that we have to get over in order to go down. So this might be our delta G here. Our delta G is highly negative, but because of this bump here, this bump we call the activation energy, which we'll talk about when we get to kinetics, is the reason. So I gave a name for this. I don't know if anybody remembers the name for this, but a mixture of methane and oxygen is not thermodynamically stable. It's kinetically stable. When something's kinetically stable like this, there's a little hump here, we call it metastable. Is that metastable means it's kinetically stable but thermodynamically unstable. And so there's a lot of metastable substances, like a stick of dynamite. Is a stick of dynamite really stable? Would you like to have that underneath your car? No. Or underneath your seat? No. A stick of dynamite is metastable. Stable. It needs something to kick it off, but it would be pretty dangerous. The same thing with firecrackers, same thing with many things. It's metastable. And we can see that. And so this question here, for which reaction below will Kc equal Kp, which equals Keq? What did you guys put? This one. C? C is correct. Delta N of gas is 0. 5.
Didn't you say yesterday that Kc would never equal Kp?
No.
But the concentrations would be for the nucleus and the pressure would be for the gas.
If I did say that, then I was wrong. I was mistaken because Kp and Kc are equal. Kp equals Kc times RT delta N of gas. I could write this out and then you could maybe see it more clearly. But the reason why they're going to be equal if you have the same number of moles of product and the same number of moles of reactant, gaseous product, gaseous reactants, up and down, because then the RTs will cancel out. But let's say, it depends on the reaction. If A goes to B, C, then I have 2 moles of gaseous product, 1 mole of gaseous reactant. And so when I do this, the RTs don't. I'll get an RT squared on top and RT to the first on the bottom, and the RTs don't cancel out. However, if I had an A plus B goes to C plus D, then they cancel out. Because I'll have an RT squared on the top and RT squared on the bottom. And so delta N of gas. If delta N of gas is equal to 0, the number of moles does not change in going from reactant to product, then the Kp and Kc are equal. This is normally talked about in chapter 15. But I had to put it in here because of Keq. So this is why chapter 15 is going to be kind of short. And so we just look for the ones. If we count up the moles here, I have 1 mole of gaseous reactants total, 1 mole of gaseous product, delta N of gas is 0, therefore Kc and Kc are equal. 6, for the reaction, methane plus 2 O2s yields the combustion of methane. Select all the following quantities that will always be the same number, 298 Kelvin, no matter how the combustion of 1 mole of methane gas is carried out. And so A, heat. We always get the same amount of heat if we burn 1 mole of methane. No? So sometimes when I burn a mole of methane, I get a little bit more heat. Sometimes when I burn a mole of methane, I get a little bit less heat. Is that true? Or should I always get the same amount? Like say, if you eat a candy bar, is it always the same amount of calories, or sometimes you get more calories, sometimes you get less calories? You know, ignoring slight variations in mass. But would it be always the same amount of calories? And so why wouldn't a mole of methane give you the same amount of heat? This is not just knowing the answer, but you know, at least analyzing why is this answer wrong? Somebody tell me why that answer is wrong.
Because you'd have a different amount of heat if it was a constant volume or a constant pressure.
Yeah, right. It depends on the work involved. So, in fact, if you burn this at constant pressure, you get more heat than burning it in constant volume conditions. Also, work, you know, depends on what kind of work you do. If you think about a CNG car, have you seen those CNG cars? CNG cars are compressed natural gas. They run on natural gas, methane. Do you think those give you the same amount of heat as your stovetop? No, hopefully not, because, you know, what you're doing on a stovetop is you're trying to convert all that potential energy just into heat. Whereas in a CNG car, you want to convert the potential energy into work, as much work as possible, you know, rather than heat. So, delta G. Always the same number? No, because it's going to depend on, well, the temperature's fixed, so it depend on what? No, delta S. Well, it does depend on delta S, but what's the primary reason why delta G would not be the same? It's going to depend on temperatures. We can't change the temperature. I fixed the temperature at 298 Kelvin. What's the primary reason delta G might not be? It could be more or less, depending on what? Okay. On the ratio, not necessarily. Not necessarily. Okay, because we don't know if it's at equilibrium. If it's at equilibrium, yeah, but Q, it's going to depend on Q. You know, if your ratio is already at equilibrium, let's say you already have an equilibrium ratio, is there any driving force for reaction? This is going to be all products. So you already got all products. Is there going to be much driving force? No. Versus, let's say you have no product and all reactants, and the ratio is going to be quite. You have no products, then there's going to be a big driving force. So it depends on your Q. So delta G, we don't know. C, delta H?
Yeah, I think that's the right answer.
On some of these, I want you to select all, so there's no one. It might be multiple, and that means you have to select multiple answers. And so, yeah, it could be correct or not. Delta H, what do you think? Well, we do make that assumption. Delta H doesn't change much, right? But we also restrict that because what we're talking about is delta H or delta H not. No, we say that delta H naught at temperature T is approximately equal to delta H naught at 298 Kelvin, which is the superscript. And so it's restricted. Here, delta H, delta H can be any. It can be, well, the temperature is going to be 298, but it could be any pressures or whatever else. And so this is not really restricted. But whereas here, delta S naught, now we restrict it. Now we're going to be under standard conditions. And so this should always be the same. However, this doesn't mean, this means we could be under standard conditions or non-standard conditions. And so it could potentially change things. Delta G? Same. So I would say D and E for this one. Would be safe. 7. This one you just, was KEQ at 400 degrees C? Anybody get the answer for this one? Hmm? What was it? So we have a temperature. We're solving for temperature. So should I use this one? T is equal to delta G naught over R ln of K. Oh no, we're solving for KEQ. Sorry, we're solving for KEQ. So we want KEQ, which is equal to E minus delta G naught over RT. So we could do this. Well, why don't you do this? Did you guys already do this? You got E? Did anybody else get E? You got E too? All right. E. How about number 8? How about number 8? Why don't you do number 8 here and then see?